All right, so let's have a look at this here. So we're going to consider a triangle with these as its vertices. So I'm going to go ahead and sketch. So I think the first thing we want to do is we want to sketch this out. So let's see. This is x, this is y. 4, -1 here, that's our point A. B is going to be at the point 5, 6. 5, 6 here. And C is going to be at the point 1, 3. Okay, so we have a triangle like this. So I'm going to go ahead and sketch this triangle here. All right, so we have our triangle. It looks something like this here. Now, I think it might be a good idea for you to just pause the video for now and just try to figure out, what do you think is true about this triangle? Okay, so we look at the triangle and we suspect, wait a minute, this looks very odd. This triangle looks like it's, this triangle actually looks very isosceles here, right? It looks like BC and CA are both the same length. And we also suspect that this looks very much like a right angle here. So, so our suspicions here is that BC equals BA. We don't know if that's true yet. We don't know if these are congruent yet. And we also have a suspicion here that BCA is a right angle. Now, do we know that? I don't know. But maybe we can try to convince ourselves that this is the case here. So we're going to run through each of these so, by the way, if these are both true, by the way, right? These are true. If this is true, if BC and BA are congruent, oh, I'm sorry, not BA, I'm sorry, this is just CA. If BC and CA are congruent and BC is a right angle here, it seems to, it stands to believe here that this triangle BCA is isosceles right. We don't know if it is an isosceles right triangle, but I think we can actually show that here. So we're going to focus on this. All right, so let's start off with the fact that BC and BA are the same. I think we can very easily show that using the distance formula here. So we're going to go ahead and do that here. So BC is equal to BA here. We don't know if that's the case here, but let's try it out. So I'm going to go ahead and sketch this out here. We can calculate the distance here. So BC, in this case here, we just use our numbers. So it's going to be 5 minus 1 all squared plus 6 minus 3 all squared. That's going to be the square root of 4 squared plus 3 squared, which is very nice. That's, I believe, 16 plus 9, the square root of 16 plus 9, which is radical 25, or 5 here. So that's BC. Now we can try BA. BA, for the same reason here, we can go ahead and sketch this out here. So BA, sorry, not BA, CA. I keep doing BA. I apologize, ladies and gentlemen. CA, we can do the same thing here. There's going to be 1 minus 4 squared plus 3 minus a -1 all squared. And that's going to be what appears to be minus 3 squared plus 4 squared, which in this case, again, is 9 plus 16. So you get radical 25, or 5 here. So note that what we have just shown here is that BC and BA are the same here. So note that in this case here, so something we can note here is that since BC equals BA, what do we know about this triangle? Triangle ABC has 2 congruent sides and is thus isosceles. So note that in this situation here, we can actually show, we convince ourselves that this is indeed the case. These are isosceles triangles here. Now, to show that BCA is a right angle, that means that we want to show that these are perpendicular here. Now, if you remember perpendicularity, you remember things about slopes. So one thing we can do here is try to calculate. We want to show that BC and CA are perpendicular. We don't know if that's the case here, but I think we can do this with slope. So let's go ahead and do that here. So the slope of BC, in this case, again, we use a slope formula. So it's going to be y2 minus y1, 6 minus 3 over 5 minus 1 here. So that's going to be 3/4. And here's the slope of AC here. We're going to go ahead and calculate that. It's going to be y2 minus y1, -1 minus 3 over 4 minus 1. And that's minus 4 over 3 here. And now we note that these are indeed negative reciprocals of each other. Or another way to think about this, you can see that the slope of BC times the slope of AC here is 3/4 times -4/3, which is minus 1, and that's what we wanted, right? So in this case here, now we note here in this situation, since the slopes of BC and CA have a product of -1, we know BC is perpendicular to CA, so angle C is a right angle. So now we note that in this situation here, this allows us to conclude here, therefore, that both of these together, therefore, triangle ABC is isosceles right, since it contains a right angle and two congruent sides. Okay? Now, note that what we have just done here, now this may seem kind of fishy to you, but you note that this actually feels a lot like a proof. And you're right, it is. Now, before you start disliking me and, taking virtual torches and pitchforks to my YouTube video here, I'd like you to think about this here. Yes, this is a proof, but note that this proof is actually not that bad, because unlike most synthetic geometry proofs, which is what you're used to over the past, several months here, much of the heavy lifting here is done by your algebra. So there's a lot of algebra here. We did a bunch of arithmetic of this stuff here with our algebra together to show that these are the same length. The same thing was true here. We did a bunch of arithmetic here to show that this is the case, and we have this together here. And basically, that's going to do a lot of the talking. But also note that I wrote out a few things here. And, the numbers are great, but they're not necessarily enough. The numbers are not necessarily what you're going to what you want to focus on here. The numbers are your evidence, but you have to create the argument here. So note that in this situation, the colored statements here, these represent just sort of backups for how or why these things work. Because these things work, therefore, this is a true statement here. So when you're writing your proofs in analytic geometry or coordinate geometry here, you want to focus on things like this. You want to show these things here using your arithmetic, and then you also want to write these statements here to sort of back everything up. You want to have a little bit of, you want to have some things to justify the calculations that you're making here. Now, of course, you could have also shown that BCA is an isosceles right triangle here. You didn't have to use slopes. Some of you may have noted, wait a minute, you could just use the distance formula. You can find the length of AB here, and if this is a right triangle, then it better satisfy the Pythagorean theorem. We got two 5s here. If I can find that AB has a length of 5 radical 2, then it satisfies the Pythagorean theorem, which implies that this is a right triangle here. So you could have also shown it's a right triangle in that version as well. No matter how you do it here, it's just a matter of figuring out what it is that you want to figure out, and then trying to put it all together like this. So basically, when you're writing out your proofs, you want to make sure that it's nice and detailed like this. You don't have to go overboard, and definitely you don't have to write it in 2-column form.